You do have a bit of a hissing on the YouTube live stream.
Yeah, the YouTube is going through OBS, so I guess the setting is a little bit different over there.
You can throw a noise gate on there to mitigate it.
Sorry?
I said you could throw a noise gate on the audio input to mitigate the
Oh,
buzzing.
okay. Yeah, part of that is coming from the buzzing noise is coming from my cable, um, because I have an extension cable, and now it's buzzing even more, and now it's buzzing less, more, less. So I guess it has to do with how I place my extension cable. Now it's almost gone. All right, we got about 1 minute left before we start the class. All right. So I'm just gonna jot down a few things, basically just announcements. So today is 2020 1203. So next week, 1 week from today, is our review for the final. So final review, it's gonna be on the 10th, and then final exam, it's gonna be on the 17th. So I'm gonna do the same thing, which is to set up a form so that you guys can let me know what time slot you are not available for the final exam. But the date is fixed on the 17th. Alright. Alright, it's 10:30. I'm gonna get started with the lecture. YouTube should be up, and hopefully the noise problem is mitigated over there. Because I just have to kind of place my cable slightly differently. I don't have a shielded cable for the extension part, and that's why it's picking up all kinds of noise, because I have a whole bunch of USB cables and whatnot around here. Alright, so just quickly going over what I wrote down here. The final exam review is going to be on the 10th, which is 1 week from today. And then the final exam itself is going to be 1 week after that, on the 17th. And I will send out forms so that you guys can indicate what time slot you are not available. So this way, I can pre-assign time slots just like exam 1 and exam 2. Alright, so that means we only got 2 days to introduce new material. Right now we are still on this particular module, big O, little o, big omega, little omega, big theta, and little theta. So last time I talked about, upper bound, how we define an upper bound, which is the big O notation. And you can see that, the big O notation is actually returning a set. So we can tell whether a particular function is a member of that set, depending on whether this expression, which is Boolean, because we are checking whether something is less than infinity. So it depends on whether this expression evaluates to either true or false. If this expression evaluates to true, then f of n is indeed a member. If not, f of n is not a member. There are other qualifications. So negligible is a special case, because if you look at the definition of negligible, it is also a element of type of relationship, with the little o notation. And if you look at the actual definition, it is similar but not exactly the same as this one over here. This is a limit superior, and this one is just taking the limit. There's a difference because this one has to converge to 0, whereas this one doesn't have to converge to a particular value. We just have to settle that the upper bound is not going to be less than something, whereas this one has to approach to a 0, so it has to converge to a single value. But you can also see how negligible is really a special case of an upper bound. So if I say if I say G is an upper bound of F, um, it is a superset of saying that G is F is negligible, relative to G. In other words, G is a gross overestimate of F. All right. So does everybody understand, why, negligible is a quote unquote subset of upper bound?
Yes.
Okay, excellent. So next we are going to talk about lower bound. So lower bound, when you look at this, when you compare lower bound versus upper bound, the only difference is, are we talking about less than infinity or are we talking about greater than zero? Okay, that's the only thing. Okay, because if you look at, well, this is also looking at the limit inferior instead of the limit superior. So we are looking at the lower bound, and we want to see if the ratio between f and g of I should say f and n, f of n versus f of g. We want to look at that ratio and see whether it is greater than zero. Okay, so we just want to make sure that it is not zero. And you can see that there's a whole lot of overlap between upper bound and lower bound, because upper bound just wants this to be less than infinity, and the lower bound wants the limit inferior to be greater than zero. So in between, there's also a dominant definition, which is a special case of lower bound, because lower bound wants the limit inferior to be greater than zero, and dominant wants the limit to be infinity, which is a special case of having the limit inferior to be greater than zero. Okay, so what we want to say about dominant is basically to say that g of n in this case is a gross underestimate of f of n. In other words, if you have an algorithm that is big O of n squared, okay, that's the actual time complexity, and you want to say, well, how does that compare to a constant time? So g of n is constant time, f of n is n squared. In that case, we'll end up with this case, because if you look at n squared divided by a constant, and you look at the limit as n approaches infinity, this ratio would also basically go to quote unquote infinity. Now infinity is not a number. We have already talked about what we mean when we say that the limit is infinity, because that is a special definition. It basically just says, if you think this number is big, I can find you something bigger. Okay, along that sequence. That's basically the idea of qualifying a limit having a result of infinity. All right, and that's it. Okay, that's almost it. Because the only thing left to do is to define what is a tight bound, which is very, very useful. So a lot of times when people say, oh, the big O of this algorithm is blah, 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 what they really meant is the tight bound. In other words, what they really wanted to say is the big theta of a particular algorithm is something. So because tight bound is very useful, because it says the upper bound and the lower bound are the same function. So that means we have a very, very good estimate of the actual time complexity of an algorithm. So when we say I suppose if big O still works, because if we say binary search, okay, if you look at binary search, the upper bound is log of n. To be exact, it's log 2 of n, but log of n is fine because you can convert any base, log of any base to log of 2 just by multiplying a constant. So in that case, the upper bound is log of the number of items in the array, but the lower bound it's still kind of like a constant, because if you're lucky and the first item that you inspect in the array is what you're looking for, that technically is still the lower bound. Okay, so that's why we cannot say the tight bound is log of n in that case. But if you qualify, the time complexity and say that, okay, we're only specifically looking at the case when something is not in the array. Okay, how can we confirm that something is not in the array? In that case, the type bound is log of n, because it will take definitely that many comparisons to confirm that something is not in the array. So when we want to use these terms, upper bound, lower bound versus type bound, a lot of times, it also depends on how we describe the original problem. Because if the original problem is to ask, what is the time complexity of finding something in an array, without any further qualification, then I cannot say the type bound of binary search is log of n. On the other hand, if I say, well, let's only look at the cases where something is not actually in the array, and we ask what is the time complexity when we already know something is not in the array, but we want to go through the algorithm. In that case, the type bound of binary search is log of n. And that's about it. Okay, that's about the end of this particular module. So it's summarized down here. If f of n is the time complexity of an algorithm, we would like to prove the big theta if possible. Otherwise, we want to find a simple function g of n, so that we find the upper bound. But we want to find an upper bound that is not a gross overestimate, because that is not going to be very helpful. So we want to avoid, okay, not so much avoid, but we don't want a big omega is not helpful, and neither is little omega, because one is a gross overestimate, that's a big omega, and the other one is a gross underestimate, which is little omega. So these two are defined within this module, but in reality, we are not really interested. Okay, if someone tells me that, oh, I can show you that f of n is an element of big omega of some g of n, I'll go like, that's good to know, but is it useful? Is this really useful information for me, so I can choose which algorithm I want to use? The answer is probably not. Okay, so that's about the end of this module, and we are moving on to the next module. So if we go back to the class, the Canvas website for this class, there are two more items here, and I'm not going to go through these two more items just because we are running out of time, and I think the important part of the big O, little o notation is to understand what each one really means. When you move on to a four-year university, you will take an upper division class called the analysis of algorithm, or algorithm analysis, kind of depending on how they want to phrase the title of the class. But in that class, they will focus on these notations a lot, and they will basically go through the mathematical derivation and whatnot in order to find what is the time complexity of algorithms. And they will probably also talk about theoretically how fast an algorithm can be. In other words, we're not even looking at a particular sorting algorithm. We're looking at what is how long would it take for any sorting algorithm to take. What is the lower bound? What is the lower bound of all sorting algorithm? And that's kind of interesting, right? Because we're not even talking about, oh, let's compare bubble sort to merge sort, or we are looking at quick sort. We are looking at any sorting algorithm, and the question is, what is the minimum time complexity, assuming the array is kind of scrambled? And the answer is actually n log n. Okay, so I'm giving you the answer already. But in that class, as an upper division for your university class, they would actually mathematically show you why that is the case. In other words, there exists no algorithm that can do sorting for less than n log n as a time complexity. So that's kind of mind-boggling, in a certain way. What we'll do now is we are moving on to graphs, because I think Iraj has already either introduced the Dijkstra's algorithm, or he's done with it already. So I'm just kind of making use of that. so that I don't have to, answer as many questions about that topic. Let's see. Oh, okay, I missed the question on the text side. The question is, can we think of supremum and infimum as floor and ceiling? The answer is no, because supremum and infimum, they do not convert a single value to something else. It is looking at a set, and it's looking at the basically the lower bound and the upper bound within that set. So I would say if you want to think about supremum and infimum, think of those two as maximum and minimum instead, because it is the maximum of values within a set or the minimum of the values within a set. So that's how I would see those. And the equivalence only works when we're dealing with something that is totally ordered. And in this case, because we're dealing with real numbers only, so we can basically say, yeah, supremum is like maximum, and then infimum is like minimum. So I can say that we can do that equivalency only because of our context. All right, so we are moving on to graphs. Okay, and I just regenerated this module. So for people who want to kind of get into how do I enter a particular equation, this one is updated, so you can right click on a particular equation, go to show math as, and then go to tech command. So now you know how to put in something. I mean, this one is not a very good example, but if you pick on something that's harder, that can be helpful. All right. So graphs is an interesting topic because there are a lot of applications. So the first thing I need to do is to define what exactly is a graph. So a graph is a two-tuple, G, which is representing a graph. It has two components. The first component is a set called V, which is a set of vertices. If you're taking some other classes or reading a book, a lot of times, people also refer to a vertex as a node. Okay, so node and vertex are interchangeable in this discussion. The other set is E, which is the set of all the edges. Okay, so now the question is, what exactly is the set of all vertices? Well, it can be anything really. I mean, your vertices can be numbers. It can be, each element in the vertex can be a set, can be a tuple, can be just about anything. Okay, there's no restriction of what element V can contain or it cannot contain. Okay, so it's just a set. Okay, that's all we know is V is a set. Each element of V is a vertex or a node. Okay, depending on how you want to name those things. But the set of E has restrictions. So E can only be a subset, not necessarily a proper subset, but it has to be a subset of the Cartesian product of V with itself. In other words, E is a set of two tuples where the first item and the second item of each tuple is found in V. Okay, so that's it. That's how we can define a graph. Okay, so within each element of E, okay, within each edge, which is a two tuple, the first item is indicating where you can start from, and then the second item is telling you where we can end up at. Okay, so this is pretty abstract. Okay, and it may be a little bit hard to kind of wrap your mind around it. So it is a good idea to kind of draw a picture. Okay, so I'm gonna shift to the whiteboard and show you a picture. Okay, it has just refreshed, so the other things that I had earlier was gone, and I'm gonna have to ask it not to suspend itself. So I'm gonna go to Auto Tab Discard and say that keep the tabs for this site, which is localhost, which is reasonable. Okay, most things on my localhost are things that are custom to me and I don't want it to go away. Alright, so I'm just boxing. Oh, Okay, that's not showing. So I'm just boxing the area, where the announcement was located originally, which has to do with when we have the final review and when the final exam is gonna be. And then now we can draw some pictures. So I just prefer to use A, B, C, D, E as the name of the vertices, because it's easy to kind of enter and easy to refer to. So here we have vertex A, vertex B, vertex C, and then vertex D. So these are the vertices. You can think about vertices as quote unquote destinations or locations or intersections, in terms of a street map. Okay, so if you think about vertices as intersections, of streets, then edges are actually segments of streets. Okay, so yeah, I can make something like this. So this is a graph, and when we look at a graph from a graphical perspective, it's pretty easy to understand because it has it has arrows. So within an arrow, so I'll just pick one arrow out of this, just so that I can refer to parts of an arrow. A is actually called the tail of an arrow, and then B is called the head of an arrow. And it makes sense, right? Because when you think about a real arrow, okay, it looks like this, and the tail is where the feather is, and the head is where the end that hurts is located, right? So that's the arrowhead, and that's why when we refer to an edge, the tail is referring to where we can start from, and then the head is referring to where we can end up at. Okay. So what we want to do with this really kind of simple graph is to turn it into a notation that only makes use of the set notation. So we can say, let's call this graph G, and it has two components. The first component is the set of all the vertices. So now we have A, B, C, and D as our vertices. And then the second one are our edges. So the edges in this case would be A, B, because there's an edge from going from A to B. And then we also have another one from A to C. So here's one from A to C. And then we have one going from B to C, going from here to here. And then we have another one going from C to D. And then the last one is going from D back to B, like so. And that is how we can define this set using the set. This is how we can define the graph using only set notation. Now, which one is more intuitive? Well, obviously the graphical representation, for simple graphs is far more intuitive compared to the set notation, because the set notation is like, oh, if I need to find out, where I can go from vertex C, I really have to kind of search through the edge set to find out, which two tuple starts with C. So it's not really very intuitive, and it takes a little bit of time to look for items. But at the same time, when you're trying to make an algorithm to deal with graphs, you kind of have to look at it from the set perspective. So that you can use a whole bunch of set primitives in order to implement algorithms. So do we have any questions about how a graph is represented, in terms of the intuitive graphical representation and also the less intuitive but more useful set notation? Do we have any questions about those two?
Nope.
Okay, thank you. Alright, so without any questions about those two, we're going to move on and talk about, very simple terms. Okay, I used to introduce all kinds of terms related to graphs, and now I just kind of condense everything to one or two. So we'll focus on what is a path, and depending on the content, depending on the definition, some people look at a path in a slightly different way, but this one will work just fine. So a path P within a graph, which is represented as G equals to VE. V is the set of all the vertices, and E is the set of all the edges. Is a tuple of vertices. Edges from E must lead from one vertex to the next. So the way I denote this is to look at this way, and it looks really kind of cumbersome, but it's not too bad. So we are looking at integers. I is a natural number, and we basically say if I is less than bar p bar, okay, so p itself is a tuple, and so the bar notation is not quote unquote cardinality. You can look at this as the length of the tuple, which is the same thing as the length of an array. Okay, so a tuple is basically an array, it's just a fancy name. So we are looking at the length of the array minus 1. In other words, I is a legitimate index into the array, into the tuple. So this first part here, from here to here, is basically saying if I is a valid index into the array, then we want to make sure that this is true. Now, what exactly is that? It's saying that p bracket I, comma b p bracket I plus 1 in parentheses. P bracket I is a vertex. P bracket I plus 1 is also a vertex within the array. And we want that to be, so we are now making a two tuple out of these two vertices, and we want to make sure that particular two tuple is an element of E. In other words, we just want to make sure that there is an edge between every two vertices within the graph. That's all we're trying to make sure. And I think I made a mistake here. Okay, the mistake is this should be bar p bar minus 2 instead of minus 1. Minus 1 is not going to work, because if you think about I equals to bar p bar minus 1, then that value plus 1 is going to index out of range. So I'm going to make a quick correction first, and then we'll continue with the lecture, because I really do not like it when I make mistakes and not fix it. And meanwhile, you guys can kind of look at all the things that we have talked about and see if you have any questions.
Is it out of range because we're counting from 0?
Yes.
Okay.
So we'll have to change bar p bar minus 1 to bar p bar minus 2. And let me publish it again. Alright, so if I refresh, then it should have changed already. There we go. So this one is correct, because all the arrays and tuples start with 0 as an index. So do we have any questions about the path? Oh, this is important too. Furthermore, a path cannot contain duplicates of a vertex. So a path is, a vertex can only appear in a path up to once. It may not be it, but if it does appear, it can only appear once. It cannot appear more than once. So are we good so far? Any questions about these terms? Well, I'm just gonna give you some examples. Okay, I'll use this picture, and we can now say, let's look at P. Well, actually, I'm gonna do that. Instead, I'll say, look at this particular tuple here. So A is a path. You go like, but we're only looking. Oh, you guys cannot see anything, can you? Oh, right, because I need to. Because I just paused the job to reuse a terminal, but I forgot to turn it back on. So I'm gonna have to. This is gonna be interesting. Because if I erase it, you will see. Okay, I just have to rewrite it. That's fine. So if you look at, no, it's still not reappearing.
What does P represent?
P is, oh, okay, there we go. It's picking up because the job was paused, but everything is buffered up. So it's P is representing a path. It's just a symbol for a tuple, and if it is, we want to know whether that tuple is a path or not. So in this case, A is a path. Okay, in other words, A as a tuple having only one item is a path. Okay, because it's okay. I mean, even though it has no edges whatsoever, we can still consider this a deformed path. So now if we look at this graph, we can look at another example. AB is a path. Now AB is also an edge in this case, but it is also a path in this case. So we can say, what about ABC? Go
How would
ahead.
A be a path if A is not a tuple?
Say it
Doesn't
about.
a tuple need to have two items?
No, it does not. Because when you look at the definition of how I qualify something as a path, so if I just look at, if P is just A, okay, having A in it, and I look at I being less than bar P bar minus 2, bar P bar in that case is just 1. 1 minus 2 is negative 1, but I is a natural number. There's no natural number that is less than negative 1, right?
Right.
Actually, I look very closely now, and the original definition is actually correct because this is a less than and not a less than or equal to. In other words, I just made something wrong again. It was originally correct, now it is not right. Does everybody see why that is the case? Because um, I I misread my own note. I thought this was a less than or equal to, um, and then if it were a less than or equal to, then bar p bar minus 1 would be wrong. But since it is a less than, bar p bar minus 1 would have been okay just fine. Alright, so I'm gonna have
So
to fix.
alternatively, you could just make that a less than or greater than to make it the same formula.
Yeah. So you can fix it one way or another, but right now it is not correct because I forgot about the that part. So I'm gonna have to change that again. I will change it back to, well, the question is less than more intuitive or less than or equal to more intuitive? I think less than or equal to is more intuitive because it's including the boundary itself. So I will do it that way. Alright, so it is updated and refresh, go to terms. So this one is correct now because I can equal to bar p bar minus 2. But when p only has one vertex, then bar p bar is 1, 1 minus 2 is negative 1, and as a natural number, I can never be less than or equal to negative 1. So that means, this is false. When this is always false and this is an implication, the implication itself is always going to be true. And that's why, a path that only has a single vertex, I shouldn't say a path. So that's why a tuple that only has one single vertex in it is a path, because it meets the requirement of this particular definition. Is that okay?
What was it before? I less than the cardinality of P minus 1?
Right. So that is also correct. I is less than bar p bar minus 1 is also correct. Because I is a natural number.
Okay, sounds good.
Okay, very good. So now that we are done with defining what is a path, I gotta give you an example that is not a path, right? So let's go ahead and look at something that is not a path. That's simple. That's pretty easy. BA is not a path because there's no edge going from B back to A, so it is not a path. And here's another example of something that is not a path. B, C, D, B is not a path. Because a tuple that has a vertex appearing more than once is not a path. Now, if you ask me, can we go from D all the way back to B? The answer is yes. So there's an edge from B to C, there's an edge from C to D, there's an edge from D back to B, which makes this a walk. Okay, there's a special term for this. It's called a walk, but it is not going to be a path because a path cannot have duplicate vertices. All right. So now we get back here. There's one more thing we need to define, and it is, I look at this as a mapping or as a function. It's called D. It maps every single edge to R asterisk. So R is the set of all real numbers, and then this little asterisk means we are excluding all the negative values. It includes 0, but it excludes all the negative value. So basically you can say we're looking at all the non-negative real numbers. So what D is doing is associating a cost for each edge. Okay, how much is it going to cost me, or what is the distance to go from one vertex to another vertex using an edge? That's what the D function is for. Okay. All right. So now that we have introduced the terms, the question now is, why are we interested in graphs? Well, if you think about a map, a city map, as a graph, okay, so, and I think it's good to kind of show a picture for that. Okay, so I'm gonna use this the right hand side area here. So we have a block here. Okay, so we're just looking at streets. And let's say this is a park. So another block, and okay, so alright. So if I want to go from one place to another place, let's just say that I want to go from here. This is where I am originally located, and I want to get to here. Okay, so this is my starting point, and this is my destination. Okay, so the question is, what is the quickest way to get there? And we can see there are many alternative ways to get there, because we can see that, we can just go straight down here and then turn here. We can turn here, then we can get down here, or we can go this way first and then go all the way straight down. So I can see at least 3 paths, going from the starting point to the destination. The question is, which way is faster? Well, it kind of depends, right? I mean, it looks like, going straight down first and then make a turn is fastest, because you don't have to make the zigzag. There's one less turn that you have to make. But then it depends on other factors like, are there traffic signs? Are there pedestrians, and so on. Path twice.
If you have A is a path, and then A is a path, and then AB is a path. Is there any
Yeah,
specific?
yeah. That's because because I suspended the process before, and things were not appearing on the screen, but it appeared on my tablet.
Gotcha.
So
So
yeah.
accidentally.
So when I unpaused the process, it picked up all the buffered movements of the stylus, and it just redrew everything in a very short amount of time. All right.
So
Okay.
would these be considered weighted paths because of the distance between each turn and each edge?
I have not heard of that term, but I suppose you can call it that. But basically, the cost of a path is the summation of the distance of all its edges. That's it, right? I mean, or you can look at the distance, but I prefer not to use distance to refer to both the cost of an edge and the cost of a path, because I would like to keep those two separated. So the idea is we need algorithms, okay, that can help us, find the shortest path between 2 points, and therefore, I mean, it makes sense, right? I mean, if you go to Google navigation, and you say, okay, this is where I am and this is where I want to go, you probably are more interested in a shortest path or a path that optimizes certain things instead of going like, well, take me through a detour. Let us go through as many intersections and go through as much distance as possible. I mean, that might work when you are a tourist, okay? You're going through a city, in which case you are not interested in a path because you're interested in a walk. So that way you can go back to the same point a few times, by using different paths, so that you can actually tour around, the city. But since we're interested in the shortest something, like the UPS truck driver is not interested in detours, but I just need to get everything delivered as quickly as possible. Now, that is not a shortest path problem, by the way. Okay, if you're a truck driver and you want to find the most optimal way to deliver packages, that is not a shortest path problem. It is called a traveling salesman problem, which is a whole different thing, okay? Because there are multiple destinations that the UPS driver has to hit. The problems that we are going to solve in this class only has one starting point and one destination, okay? That's all, okay? So as it turns out, there are two algorithms that can, help us with this. The first one is called Dijkstra's algorithm, and if you're taking or have taken CISP430, you would have known something about this algorithm already. And if somebody says, but I have not taken CISP430 and I'm not taking CISP430, then I'm going to have to say, well, that's the co-requisite of this class. Okay, so I'm going to continue to make the assumption that people already know Dijkstra's algorithm from CISP430. Alright, but the way I describe it is slightly different in this class, so we're going to have to go through this kind of gradually, but I would assume that people already know the general idea of Dijkstra's algorithm. So we're going to go through the algorithm first and kind of briefly explain what each line is trying to do, and then we will trace it, okay? Because the best way to understand an algorithm is really just to walk through it using an example. So the first line is nothing more than just defining the terms. G refers to the graph, which has a set of vertices called V and a set of edges called E, okay? Pretty standard stuff. D is a function that maps edges to their distance. So, every single edge has a non-negative real number associated with it as a distance. So, nothing new here. The second line is different compared to how Iraj or other people teaches Dijkstra's algorithm. Because this one says you have a subset of vertices called S, and they are the destinations. Those are the places where we want to be. Or I want to be at one of those places. Okay, so this one is different, right? Because when Iraj teaches Dijkstra's algorithm, he would only have one single destination. But this algorithm says, hey, I can deal with multiple destinations. So now the question is, why is that helpful? Okay, why do we want to have multiple destinations? I got one simple answer for you. Think about a theme park. Okay, think about let me think of one. Six Flags. Okay, Six Flags in Vacaville, and you are taking a 3-year-old with you. Okay, to a theme park, and obviously, the 3-year-old needs to go to bathrooms. Okay, like many times a day, and so now the question is, you're at a particular place, okay? You just watched the killer whale, show, and the 3-year-old says, "I need to go to the bathroom fast," okay? So now the question is, where is the closest bathroom, right? Because Six Flags has more than one bathrooms, but in your case, you want to go to the one that is the closest, okay? The one that will take you the least amount of time to get to. That is why it is helpful to have multiple destinations, and you just want to find the shortest path. Well, actually, in this case, Dijkstra's algorithm will find the shortest paths to all of the destinations from a single point of origin. So this algorithm is a little bit different from how Iraj explains his, but it has the advantage. It doesn't take any longer to run, by the way. Okay, but it will give you multiple shortest paths. Go ahead.
I have a question about the how things are written. So for the D colon E pointed to our pointer, that is for D and E, where E is our real numbers, correct? Is that how?
It is a function description. Yeah. So if you go all the way back to the discussion of functions, D is the name of a function, E is its domain, and R star, which is the non-negative real numbers, is the codomain.
Oh, okay.
So I'm just reusing that notation to define what is the domain and what is the codomain of a function. Are we good?
Yes.
Okay, excellent. And then the third line says, let's do some initialization. Okay, so for every single vertex that is a destination, we are going to define L of V to be 0. Okay, that's just how we define it. Now, it is also important to understand what is L of something. L of a particular vertex is the length of a path from where you are, from the point of origin to one of the destinations. Okay, so let me repeat it. Okay, L of something, L of V, is representing the length of the shortest path from the point of origin to one of the destinations. Well, what if V itself is already a destination? Well, if V is already a destination, then we can say, hey, we are already at the destination. Actually, I take it back. Darn it. Okay, I said it wrong again. L of V is representing the length of from a shortest path from V to one of the destinations, not from the point of origin. That's when I got wrong. Okay, L of V is the length of the shortest path from V itself to one of the destinations. But if V itself is a destination, well, then I don't have to go anywhere because I'm already at the bathroom. Okay, so the 3-year-old can go to the bathroom right away because we are already right next to it. Is that okay?
Yes.
Okay. And then what about the rest? Okay, what about all those non-destination vertices in V? Okay, that's going to be initialized on the next line where we say if V is in V minus S, okay, in other words, V is a non-destination, we'll initialize L of V to be infinity. In other words, well, I do not know whether there is a path, okay, from V to one of the destinations, because you can end up with a graph where you cannot get to a destination. So we'll make that assumption first. We'll basically say until I find a path, I'm going to assume the length of that path is infinity. In other words, I'm assuming there's no such path until I find one. So that's why L of V is defined to be infinity, because I just got started here. Okay, I really do not know whether there is a path leading from vertex V to one of the destinations. And then the next line initializes set Q to be the set S. In other words, we're starting with the set of all the destination vertices, and we'll work our way back to all of the other vertices. Okay, so this is really cool because you don't even have to know where you are. There's no single starting point. This particular algorithm will find the shortest path from every single vertex in V to to a destination that is closest to it. So you just have to do this once, okay? Imagine you have a trip to Six Flags, bringing a 3-year-old. You can do this before the trip because the result of this particular algorithm will basically point you. It will give you the shortest path from every single point on the map to the shortest destination on that map. So if you're looking for the little boy's room, okay, it will basically say from every single intersection of Six Flags, it will show you how to get to the closest little boy's room. Okay, so it is a really fun and interesting algorithm. It will give you multiple solutions. And we also initialize E prime to be an empty set. This set is going to be a subset of E, and it is going to be the set of all the quote-unquote solution edges. And then the actual algorithm, okay, when you look at the control structure, the actual algorithm starts from here, starting with a while. And I'm doing this, kind of pseudo Python style. Basically the indentation is indicating the nesting of the statements. So the while loop is the overall control structure. The first thing we do, okay, so the while loop says, is Q an empty set or not? If Q is non-empty, then we're going to go ahead and start to do whatever is in the loop. The first thing we do is to look at all the elements in Q, and we want to find one so that it has the least L value. In other words, we're looking at the one that has the shortest distance to a destination, and we go like, okay, I know amongst all of the vertices in Q, you are the one that is the closest to a destination, so I'm gonna start with you because I want to consider, okay, other vertices going through this this particular vertex V to get to a destination. Let me see if I can find an analogy to explain this. Okay, you can look at it this way. If you look at Q as people with money, okay, and you're trying to borrow money, then you're looking for the richest person within that collection, because it is likely that that person is going to lend you money, and then you chain this whole thing back. So you have people who borrow money from somebody else, and then you have people borrowing money from that person, and so on. I'm not sure that's a good analogy or not, but by the time we get to a trace, it'll be clear why we are doing this. So anyway, once we select V, out of Q, the next thing we do is we remove V from Q, so that we make sure that we do not consider the same vertex again, unless there's a good reason. Okay, so there are times when we go like, oh, by the way, we need to reconsider the vertex that we have already considered before. Okay, so there are cases like that, but in general, okay, once you select something and say, this one looks promising, you take it out of Q. The real expansion part is this for each loop. In other words, what we do is we look at e, lowercase e, and we basically are looking at all the edges that can lead from a vertex W to the vertex V that we have selected here. So we're looking at all the incoming edges into vertex V, because all of those vertices can go through V to get to a destination, because V already knows how to get to a destination. So all the vertices that connect to V can also now go through vertex V to get to the same destination. So just for the shorthand, we basically say E is WV, so W is the start vertex of that edge, and then V is the destination vertex of that edge. So we now compare and say, okay, we already know, what is the length of A shortest path from V to one of the destinations. We also know the distance from W going to V. So when we add these two, okay, it becomes the length of a path going from W to a destination. But we want to see if that is less than the currently known, or I should say, we want to compare that to the length of the currently known shortest path from W to a destination. So I'm basically saying, okay, we might have discovered a path from W to a destination already, which has a length of L of W. But now we're finding a alternative path from W going through V to get to a destination. I want to compare these two paths and see which one is is shorter. So if I do indeed find a shorter path going through V to get to a destination, then the first thing I do is to update L of W, because I just found a shorter path that has a length of L of V plus the distance of the edge. The edge that we are talking about is going from W to V. And then what we do is we take it out of E prime. Okay, we take the old edge out of E prime. So we remove every edge, from W to any vertex out of E prime, which is the solution graph, the solution edges, and then we add it back to E prime. But we are not adding just any edge starting from W into E prime. We're adding that specific edge that will go from W to V into E prime. And then what we do is also to add W to the set Q, because now W has a shorter path to go to a destination. So all the other vertices that can go from that can get to W with one single edge, they might have a shorter path now, and that's why we add W to the set Q. And when this is all done, when this while loop is done, then we define the solution graph to be G prime, and G prime would have the same vertices, but the edges is not E anymore. Instead, it's going to be E prime, and E prime is guaranteed to be a subset of E. It can be a proper subset, but it doesn't have to be. So that's an overview of the algorithm. We got about 25 minutes left, so I think we have enough time to trace it. But I have to think about how to how to get the trace represented, and I think a spreadsheet is probably the best way to do it. So we'll go ahead and use a spreadsheet. So let's go to G numeric. All right. But before we get to the trace and use the set notation, it's probably helpful to use a pictorial or graphical representation of the graph that we want to solve. Let me start a new page first. And refresh this side. Alright, so let's look at one that is kind of interesting. And we'll have A, B, C, D. So A going to B has a distance of 2. B going to C has a distance of 2, and then C going to D has a distance of 2 as well. But that's not going to be very interesting, right? Because this is just linear. I mean, the algorithm is going to be, it will process this in a very easy way. So in addition, we'll have an edge going from B to D, and it is going to be a longer one. So I'm going to put a 6 over here. And we'll also have one edge going from A all the way to D, and this one is even longer, and we'll make this an 8. And let's make this even more confusing by introducing a, well, actually, no, it doesn't have a loop yet. So we'll go ahead and introduce a loop here, and it's going to go from D back to B, and this edge has a cost of 0. Okay? And we're not going to work with multiple destinations in this case. We'll just work with one single destination. So our destination set has one particular element or one particular vertex in it, and it's D. So this is the starting point of this particular graph. And the first thing we also want to do is to encode this in a way that our algorithm can handle. In other words, we want to look at this from the set perspective. So what we'll do is I'm gonna use my spreadsheet on the side here, and we'll go ahead and define what V has. So V has vertices A, B, C, D. The set S only has one single element, which is D in it. The set E, which are all the edges, has AB, has BC, CD, DB, BD, and AD. There we go. And the distance is going to be a set of two tuples, where the first one is an edge, the second one is a real number. So AB is the edge, and it has a distance of 2. BC is, okay, one more open paren. So BC is the edge, it has a distance of 2. CD is an edge, it also has a distance of 2. DB is our edge, it has a distance of 0. And then BD is our edge, it has a distance of 6. And then AD is our edge, it has a distance of 8. So I'm converting the graph so that I can just use set notations to represent everything. So now that we have this defined, I have to follow the algorithm. So I'm gonna put this on the side, and we get back to the algorithm. Okay, so that we can actually follow the algorithm on this side. I'm just looking at this, and okay, we can just overlap a little bit, okay, because the algorithm is much longer than it needs to be, because I also put in comments to explain what each line is doing. So those do not need to be around for too long. And also I can break the screen into 2 parts. Okay, so I'm going to put all the initial conditions on the top bar here, and get rid of these 2 rows. I'm gonna set this up so that I have one portion of the screen that I can scroll through, and then the other portion stays put. Alright, and then to maximize the area, I can turn off all of the toolbars. Okay, so we'll get rid of the toolbars. I mean, frankly, who uses toolbars, right? There we go. So now we have a little bit more area for putting our actual trace. And I need to, oh, this is G-numeric. It doesn't have a way to break the screen into 2 scrollable portions. Okay, well, that's fine. We'll find a way to get around that problem. Alright, so we have a few things that we need to track. Okay, this column A is going to track Q. This column here is going to track which vertex V we're dealing with. And this one is going to track which W that is going to V, okay? And then this one here is going to track L. Basically, L is going to be a function, so it'll be clear what it's going to look like. And this one here is going to keep track of E prime, which is the solution edges. Alright, so the first thing we need to do is to initialize the L values. So every L value is going to be infinity except for the L value of a destination. So when you look at L, it is as a function, it's going to map A to infinity, it's going to map B to infinity, it's going to map C to infinity, and it's going to map D to 0, because D is the destination, and only destinations have a 0 as a starting value. And I have to be mindful of what you guys can actually see, and I think everything is still good except for the closed curly brace of E, and that's going to be okay. And E prime is initialized to an empty set. So initially we say we don't even know whether the destination is reachable at all. So we really do not know whether there's actually a reasonable solution. So that's the initialization. Row 4 is representing everything that we do from line 1 to line 4. Now I can also combine the initial Q, which is just the set of all the destinations, which is D, and now we have everything initialized, and we can start the loop. So the loop says, let's take a look at Q. Is it empty? Nope, it's not empty. And now we need to select a vertex V in Q such that blah 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 blah. Okay, but the blah 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 is not important in this case because there's only one vertex in Q, so we don't have to choose. Okay, if you only have one vertex in Q, it's gonna be the one that is going to be chosen. So vertex V, and it doesn't need to be a wide column, so I'm gonna shrink this a little bit so that we have more space to the right hand side. So we choose vertex D to be coming out of set Q, and the next line says let's remove that same vertex from Q. So Q becomes an empty set for the time being. Okay, doesn't mean it's gonna stay empty when we get back to the beginning of the loop. And now we get to the for each loop. So the for each loop is looking at every single incoming edges into vertex V, which is our vertex D. And and then for each incoming vertex, we look at that particular neighbor of V and ask, well, have we found a shorter path for that particular vertex? So at this point, it is helpful to look at the graph again, because we want to look at vertex D and ask who can get to vertex D. Well, vertex D is actually pretty popular. A can go to vertex D, B can get to vertex D, C can also get to vertex D. So that means when we trace the algorithm, this particular for each loop is going to have 3 iterations. One iteration for vertex A, one iteration for vertex B, and one iteration for vertex C. Now the question is, well, does it matter, how we get through those vertices? And the answer is no, it doesn't really matter. We can just traverse, those vertices as vertex A, B, and then C. We can go in a reverse order, C, B, A, and any order is fine. Okay. So we'll make this kind of randomized. Okay, we'll start with B first. So now the question is, have we just found a shorter path for vertex B to get to a destination? So we have to go through this line here. We are looking at this line here. So we are looking at the current L of W, which is L of B. L of B at this point is infinity right here. Okay, it is infinity. So that is telling us that, hey, anything that is not infinity is going to be shorter. So we look at L of V. V is D. L of D is 0. So we have a 0 plus D of E. E is the edge, going from B to D. So if you look up the distances, going from B to D has a distance of 6. So we are now looking at 0 plus 6 and comparing that and see if it is less than infinity. The answer is yes, it is less than infinity. So now we get to the then branch of the conditional statement, and the first thing we do is to update it. So this is going to look, it may not be very clear, okay? But what we're doing is now we say, hey, we just found a shorter path going from vertex B to a destination, and that path is going to have a distance of 6. Okay? But we also have to say, since we just update the length of the shortest path from vertex B to one destination, we need to put B into Q now, because all the incoming edges to B are now interesting, and I need to investigate all of those. And, well, now we have vertex A or B to look at. Let's go to A, okay? So we go through the same motion and see if we have just found a shorter path from vertex A to a destination. And the answer is yes, we did. Because from here, we can see that the shortest path from A to a destination has a length of infinity. And now we say, but hey, we can go from A directly to the destination because there's an edge from A to D directly, and that edge has a distance of 8. So we have just found a shorter path. So we go from here, we copy and paste it, and then we change the infinity this time to an 8. Okay? But that means we have just updated the L value of A. So now we have to put A in the set Q as well. And now we get to C, which is the last vertex that has an edge going to vertex D. And then we ask the very same question. Okay, have we just found a shorter path going from vertex C to a destination? Before we say, oh, I forgot important things. Okay, I forgot to put all those solution edges into E prime. So we have BD, in E prime, and then we have BD as well as AD in E prime. And then by the time we get to C, it's gonna have, it's gonna do exactly the same thing. C can go to a destination directly now, and it has a distance of 2 this time. All right. Oh. Okay. So it has a 2 as a distance this time, and we have to add the edge from C to D as a solution edge, at least for the time being. But because we just changed the L value of C, we have to investigate all the incoming edges to C as well, because maybe those other vertices would have found a shorter path at this point. So by this time, we are done with the for each loop because we have looked at every single incoming edge to vertex D. So we exit the for each loop. And now we are back to the while loop. The while loop is asking, is Q empty? Nope, it has got 3 things in it. Now this time, when we get into the loop body, we have to select the V with the least L value. This time it is important which one we choose as V, because out of the 3, A, B, and C, and when we look at the L value, A has an L value of 8, B has an L value of 6, C has an L value of 2, so C is the one that's going to be chosen because it has the least L value. And now we get to, we have to remove C from Q, so Q only has one A and B left. Now we have to look at all the incoming edges to vertex C. So when we look at the edges from going to C, there's only one single edge, which is the edge BC. So we look at the edge BC, and now we ask the question. We know to get from vertex C to a destination, the shortest path has a length of 2. We know that because L of C is just 2. So now we look at the distance from of the edge BC. So according to the D function, the distance going from B to C is also 2. So 2 plus 2 is 4. So that's the left-hand side of the comparison. And we're comparing that to L of W. So we are comparing to L of B, which is 6. 4 is less than 6. Oh, okay, so we have just found a shorter path from B to a destination. So the first thing we do is we update the L value of B so that it goes from 6 to 4. There we go. And then we remove, the edges that start from B in E prime. So when we look at E prime, we're going to have to get rid of BD because we have just found a shorter path that is not going through the edge BD. Okay, so BD is not representing a part of the shortest path anymore from vertex B to the destination, and instead it is going from B to C first, then from C to D. So we are basically, I'm combining these two steps. I'm combining the step to remove an existing edge and also the step to add a new edge. But we also have to make sure that B is staying in the set, but that's okay. There's no actual change in this case because B is already in the set of Q, so we don't have to do anything special here. That concludes the for each loop because there's only one edge going from B to C. Let me just double check. Yep, BC is the only edge going to vertex C. So we are now done with the for each loop, and then we go back to the while loop here. So the while loop is asking the same question, as last time. Is the set Q empty? The answer is nope, it is not. So of the two elements left in Q, we look at A and B, and we want to know which one has the least L value. A has a L value of 8 at this point, and then B has an L value of 4 at this point. So B is the one that has the smallest L value, so we select B to be our V, and then we ask, okay, give me all the incoming edges of B. And I believe B has 2 incoming edges. One is coming from D, and the other one is coming from A. So we got AB as an incoming edge to B, and then we also have DB as an incoming edge of B. Let's look at DB first. Okay. In other words, have we just found a shorter path from D to a destination? Well, let's go through the calculations. L of V is L of B, which is 4. D, the distance of that edge is also 0. Okay, because we are looking at D of DB. So that is also a 0. So that's a 0. So we have 4 plus 0 on this side. But when we look at what is L of W or L of D, it is 0. So we haven't found a shorter path. Well, it's not really surprising because D is a destination already. Okay, why do I want to go from a destination to another vertex and then back to the destination? It doesn't make sense, okay? So we are done. So this time we do not have any updates because the condition of the conditional statement is false. So now we don't have anything else to do, but we also have to remember everything we choose something, we have to remove it from the set. So now we are back to the while loop because we have only one single. Oh, wait. Okay. I take it back. There's another edge going to B, which is AB. So now we have to consider the edge AB. The edge AB itself has a distance of 2, and the L value of B is 4. 4 plus 2 is 6. So we have the left-hand side of the comparison being 6. The right-hand side of the comparison, L of B, is L of no L of A, because we're considering W and W is A at this point. L of A is 8. 6 is indeed less than 8. So we have found a shorter path from vertex A to a destination. So now we have to go through all the updates. So that this time we have to register. We have to change L of A from 8 down to 6. And then we have to adjust the edges as well, because everything that is going from A to something, it has to be removed, and it will be replaced by AB in this case. And we also have to add vertex A to Q, but it already is in it, okay? So there's no actual change to the set Q. So after all of this stuff here is done, we're now done with the for each loop, because we have just examined every single incoming edge to B, and now we go back to the outer loop, the while loop. Is Q empty? The answer is no, so we have to go into the loop. But since it only has one single element, there's nothing really to compare to, so we just say, okay, well, since A is the only thing left, we're gonna have to choose it. And now the set Q becomes empty. And now we look at all the incoming edges to vertex A. In other words, we look at the set E and we ask, okay, who can get to vertex A? None of them, okay? So there's no W. The for each loop inside the while loop has 0 iterations this time, because we do not have any incoming edges into vertex A. So now we get back all the way out to the while loop. The while loop is looking at Q. It is empty this time. There's nothing else to do, so we get out. So now the question is, okay, so the algorithm is done. What is the solution? Okay, what have we identified as the solution? The solution is E prime being BC, AB, and CD. So I'm going to pull this off screen for the time being, and then go to my tablet side, and this time I can now show you what it's going to look like. Okay, I have to wake up the tablet first because it just fell asleep. So BD is, oops, did I make a mistake? BC, that's right. So BC is one of the solutions, so I'm just gonna make this line thicker. AB is part of the solution, so AB is part of the solution, and then CD is also part of the solution, and that's it. So the thicker lines in the graph are the solution. So, or if you prefer, you can redraw the picture. So you have A going to B, going to C. This is our solution graph. If you are starting with vertex A, go to vertex B, and then you can get to the destination. Okay, I'm missing the last one here. Okay, if you are starting with vertex B, you go to vertex C and then go to vertex D as your destination. If you're starting with vertex C, you go to vertex D with a single edge. So this is kind of interesting in a way, because if you think about it, okay, if you're starting with vertex A, you have one single edge that will bring you to the destination right away. But the distance of that single edge is really long. It is 8, which is more than 2 plus 2 plus 2. So the number of hops is no longer a major consideration. It is the summation of the distances of all the edges that matters. Okay, so even though I made a graph like this to try to trick Dijkstra's algorithm to misidentify, AD is the shortest path from A to D, it realized that that was not the shortest path, because you can see when we updated from we updated L of A from infinity to L of A being 8. This is the first time, but we updated again over here as we found a shorter path from A going through vertex B to get to the destination. So this is Dijkstra's algorithm. Some people call this the modified Dijkstra's algorithm. I really don't know. I mean, it seems to make sense because it's not much more expensive compared to the normal Dijkstra's algorithm, and it finds the shortest path from every single vertex to a destination. So it's kind of cool in that way. And guess what? We are out of time. Perfect timing. So over the weekend, I want you guys to kind of experiment with Dijkstra's algorithm. I can give you guys a sample graph to work on, okay, with multiple destinations. So you can work on that, and well, yes, maybe I'll turn it into a homework assignment too, okay? But it is important for you to kind of go through this, by hand. Um, if not for anything else, you can always use the graph that I just worked on, okay? But I will give you a new one, to work on too. But also, before next Tuesday, I want you to read the A star algorithm. There are some concepts here with the A star algorithm that we haven't really talked about, but it's explained within this section here. It has to do with um, a heuristic function, which is a kind of like an estimate. Okay, between what is the distance of a path between two edges, between two vertices. It's called a heuristic, and that's a new thing to the A star algorithm as compared to Dijkstra's algorithm. So that part is new. It might take you a little bit of time to kind of read through this, okay? But I still want you to read as much as you can. This is a slightly longer, algorithm, not by much, just a little bit longer. But I want you to read this, basically finish reading this entire module before Tuesday, and then on Tuesday I will explain the A star algorithm using an example like what we're doing today, but it's going to need the heuristic function defined as well. So that's kind of the game plan. Next Thursday, we'll have a final exam review. The final exam will cover everything to these two algorithms. So we are a little bit tight on time, but hopefully we can get everything done. All right. So do we have any questions? I'm looking at Discord. Oh, I think I missed a direct message. Oh, but that's not coming from the class. Okay. All right. Yeah, go
So
ahead.
the last lecture will just be more on graphs.
Yes. So the last lecture is going to be next Tuesday, and we are just going to finish the A star algorithm, and that will be the end of
Okay.
all the lectures.
Okay, so we won't touch predicate calculus.
Yeah, we're gonna miss that. I can give you guys an extra lecture, but I cannot put it into the final exam. But I will put I will make a recording of predicate calculus because I think it is interesting. Okay, there are a few things you can do with it, especially in prologue. That is kind of fun. But since I don't have time to cover that in one of the lectures, I cannot put it into the final exam.
Okay, yeah, that works out.
Okay.
And
Mm-hmm.
I felt like just mentioning something that's a little interesting. The way Sapsaveri did the lecture on Descartes, the
Dijkstra.
algorithm,
Mm-hmm.
Dijkstra, it kind of went backwards. It started from the starting
Yep.
destination to the
Mm-hmm.
end destination.
Yep. But does it work with multiple destinations or just one?
Just one.
Just one. Yeah. So his algorithm has one starting point, has one point of origin, and only one single destination. This one can handle multiple destinations and will figure out the shortest path of every vertex to the shortest to the destination that is within. How should I put it? it will figure out the shortest path between a vertex and one of the vertices. That would be the best way to put it. So it will give you a complete solution and not just go from one vertex to a destination.
Yeah, I also felt it was more intuitive too, starting from the where you want to
Destination.
be and going backwards.
Well, you can go either way, but because we have multiple destinations, so sometimes you will have an update because you start from one destination, you get back to a vertex, and then later on you found that hey, if I start from another vertex, it's actually shorter to get to the same vertex. So it gets kind of interesting, but it's Dijkstra's algorithm is really easy to analyze in terms of the time complexity because we never revisit an edge twice. So that means the number of edges is the upper bound of the time complexity. The cardinality of E is the upper bound. All right. So I'm gonna stop the lecture at this point, and I will work out an example for you guys to work on over the weekend. So that will give you something to kind of practice. And then on Monday, I will talk about the solution of that graph. But I'm going to post it in the text channel here on Discord. All right. Have a nice weekend. And I'll see you guys next Tuesday, which is going to be our last lecture. All right. I'm just going to stop the streaming now.